Hi, I'm Kim J. Due to unforeseen circumstances, my collaborator, Femi, is unable to join us. However, do stay with me because we are really excited to share about the statistical finite element method. This has been a very active project involving contributions from several colleagues. There are Eki Fabrianto, Mark Girolami, Jiyin, and Dennis Akildis. In this video, I will talk about the statistical finite element method and a promising extension based on stochastic partial differential equation approach that improves the scalability and modeling capacities of the statistical finite element method. To start with, finite element models for design of engineering systems are often misspecified. Inherently, there are uncertainties in the materials, geometry, loading, and so on. At the same time, increasingly, there have been more and more operational data from advanced equipment. This motivates us to blend together this measurement data and finite element models to make more reliable and accurate prediction. Our objective is to develop a statistical framework that coherently synthesizes data and finite element models. Here is a real-life example of a bridge in the UK. This bridge serves as a real system. By placing some sensors at some locations of this bridge, we can collect measurement data, for example, strain data, and we have a finite element model of the bridge. And the objective is to make finite element predictions conditioned on the collected data. In terms of challenges, of course, the finite element models are misspecified because of the inherent modeling assumptions and uncertainties. In addition, we need to bear in mind that in the field of engineering, data is relatively scarce compared to, say, the field of computer vision and language processing. Hence, we really need to take these constraints into account. Many of you are familiar with Bayesian inference. Our approach is also Bayesian or probabilistic, so that we have some random variables. These random variables include the real system response, a vector z, the finite element nodal response, a vector u, the data, a vector y, and we assume that these data are corrupted with some measurement noise, e. Here is an illustration of these random variables with only one single degree of freedom. I'm really glad that you are staying with us. Now, I will continue by reviewing the statistical finite element method. Then, I will present a novel approach to improve the scalability and modeling capacities of the statistical finite elements. And finally, some illustrative examples. We assume for the statistical model that the data vector y is composed of the true response z and an additive measurement noise e. Then we further assume that the true response z is composed of the finite element response u and some mismatch random variable or discrepancy vector d. Here P is just a projection matrix that projects the finite element response to the space of the data or the true response. Rho is a scalar hyperparameter, just for scaling this. In this work, we assume that all the priors and likelihood are Gaussian. Hence, the probability densities of all these random variables are fully defined with some mean vectors and covariance matrices. As a representative example, let us consider a probabilistic forward problem where the governing equation is a second-order elliptic partial differential equation, the Poisson equation. Here, the coefficient mu and the source f are assumed as Gaussian random variables. Usually, the finite element solutions and the respective prior densities, they can be obtained by, for example, Monte Carlo sampling, polynomial chaos expansion, and here we use the first order perturbation to determine the finite element prior. When specifying the finite element prior, we need to bear in mind that the finite element models contain assumptions which result in irreducible misspecification or discrepancy. As we have discussed earlier, this discrepancy can be represented as a random vector D, which is assumed to follow a multivariate normal distribution with the mean vector 0, and a covariance matrix CD. In this work, we parameterize the covariance matrices using the Mattern kernel for reasons to be clear later on. If you're not familiar with the Mattern kernel, you can think this as a variant or a generalization of the square exponential kernel. For example, the hyperparameters sigma, which is the standard deviation, and the length scale L are also seen in the square exponential kernel. Nu is a hyperparameter that controls the smoothness of the random samples. To make finite element predictions conditioned on the data, we can use the Bayes rule to obtain the posterior density. Again, the likelihood of the data and the finite element prior are assumed to be Gaussian. In addition, they are conditioned on a vector of hyperparameters called W. So we know that the product of two Gaussian densities yields an unnormalized Gaussian density. Using some analytical formula, we can easily derive the posterior mean and the posterior covariance. The important takeaway that I would like to highlight is that if we have a large finite element model, then these matrices are generally costly to invert here. And I will talk about this in a moment. The denominator of the Bayes rule is known as the marginal likelihood or the evidence, which tells us how probable it is to observe the data given some finite element solutions. Hence, the intuition is that we want to select the hyperparameters in such a way that the marginal likelihood is maximized. This is also known as the maximum likelihood estimates, and we use this to learn the hyperparameters. And this really just involves standard optimization routine. Once we have obtained the optimized hyperparameters, we can substitute them into the posterior densities to make predictions. As an illustrative example, here is a one-dimensional Poisson-Dirichlet problem with random forcing. As a prior belief, we may assume that the random source is a Gaussian process with a constant mean, and its uncertainty may be described by a square exponential kernel listed here. Now we solve this PDE using finite elements, and we get the finite element prior solution indicated by the blue color plots here. The solid line here represents the mean of the random solution, whereas the shaded area represents the 95% confidence interval. Unfortunately, our prior belief may not be accurate, right? For example, the underlying true system solution may actually look wiggly as given by the black color plots here. To see if we are able to infer the underlying true system response, we select some locations for the observations and generate synthetic observations by sampling from some underlying data generating process, which is a Gaussian process. You can see that this is essentially the true system response with some additive Gaussian noise. And at each of these observation points, we further create some repeated readings. And the purpose is to see whether we can learn better when we have more and more data. Here is the result of the posterior finite element density, as highlighted in red here. As a reference, we have the previous prior finite element density in blue. So these are the mean of the random solutions. And the dots represent the observations. So we can see that as we increase the number of data points NY, or when we increase the number of repeated readings at each point NO, we can see that the posterior mean convergence to the mean of the data generating process. Although it's not shown here, the variance actually also converges to 0. So similarly, we can also infer the underlying true system response Z, and you can see that the same behavior is observed here. To give a summary so far, the idea of the statistical finite element method is that data and prior densities, they are combined through the Bayes rule to infer the true system response. And we have seen earlier that the posterior mean and the posterior covariance, they involve expression of the dense covariance matrices. We know that dense covariance matrices are costly to invert. Therefore, implementation-wise, this is only suitable for relatively small finite element models. Our solution to that is that we express all the probability densities with precision matrices, because this precision matrix is the inverse of the covariance matrix, and it turns out that they are sparse, which means they have the Markov property. And it turns out that the Merton precision matrices, they can be expressed simply as a stiffness matrix of some fractional stochastic partial differential equations. The stochastic partial differential equation turns out to be a linear partial differential equation with the fractional order beta. Here, f hat is the Gaussian white noise, and u hat is the Merton random field. This is really interesting because apart from the analytical expression of the Merton kernel, we can actually define Merton field by means of solution of the SPDE. Indeed, there is a one-to-one correspondence between the parameters in the Merton kernel and the parameters in the SPDE. For example, the fractional order beta is related to the new parameter of the Merton kernel. Now, recall that the new parameter controls the smoothness of the random samples. So when we increase the value of nu, you can see that the Merton covariance function changes and the samples actually get smoother. Now we know that we can obtain Merton fields in a very different way. How is that useful? And the usefulness of this is that it turns out that we can actually derive the expression of the precision matrix from this SPDE. So now I will consider SPDE with some integer beta so that this is much simpler. So given an arbitrary integer valued beta, we can actually obtain a recursive solution using this form. And the idea is that you can solve a linear PDE of a lower order and then recursively obtain solution when the beta is large. So let's take beta as 1, and using finite element discretization, we can obtain this linear system. And this is the random forcing, the Gaussian white noise, which gives a covariance matrix of M, where M stands for a mass matrix. And the precision matrix turns out to be expressed in terms of some finite element matrices. So L here stands for the linear stiffness matrix, and M here is again the mass matrix. And because these matrices are finite matrices, they are sparse and they are banded. So the multiplication of them is again sparse and banded, and hence we obtain a sparse precision matrix. So this is important. The precision matrix is sparse, although the covariance matrix is dense. And once we have obtained this precision matrix for higher integer beta, we can just recursively compute the corresponding precision matrix. In general, however, beta is fractional valued. Without going into the details, our general idea is that we approximate a power function x to the power of beta using rational approximation. In the theory of interpolation, rational approximation is more accurate than, say, a Taylor series expansion. And here is an example of rational approximation of the function x to the power of 0.5. And you can see that it's generally very accurate. Then the key idea is that we can then replace x with the operator L and derive the expression of the precision matrix. Let's walk through some illustrative examples. The first application that we consider is a Gaussian process regression on a hemisphere. There are two advantages exhibited here. First, we can really upscale the finite element model up to, say, 1 million linear elements in this example. In addition, in the context of Gaussian process regression, the data size can be also upscaled, and hence this greatly improves the scalability of the GP regression. The second advantage is that the method field turns out to be naturally defined on this curved surface. In other words, we don't have to worry about computing the distance on this curved surface. In this example, we have selected some observation points and generate some syntactic data from this true function. And you can see that the inferred mean generally converges to the true function when the data size is increased. The second example is the statistical finite element analysis of a Poisson problem with random source on a 2D domain, which is a plate with a hole. So similarly, the source here is misspecified. So what this means is that the true solution that we assume here is actually different from the finite element prior that we assume. So as you can see here, not only that the scale is different, there is also some missing physics along the corners of the domain. So we want to infer the true solution given some data, and we generate this data by discretizing the domain up to 800,000 elements, and we do inference from this data. So you can see these are the first solutions for different number of measurement points. In general, you can see that when we increase the measurement points, the inferred true mean converges to the underlying true mean. And here shows the uncertainty estimate, and these are the standard deviation plots. The third example is about modeling non-stationary and anisotropic random fields. Typically, the method field is stationary and isotropic. However, we can also obtain method fields that are non-stationary and anisotropic. This extension can be very easily done by modifying the stochastic partial differential equation that we have seen earlier. So for example, we discretize the bunny surface with 1 million triangular elements. So at the top, we show the non-stationary correlation function and its sample. At the bottom, we again show a similar stationary anisotropic correlation and the random sample. To summarize, we have introduced a statistical finite element framework for coherent synthesis of observation data and finite element models. The Bayesian framework can be interpreted as a physics-informed Gaussian process regression technique, of course assuming that the prior and the likelihood are Gaussian. There are several possible extensions, such as model selection and comparison. In the second part of the talk, we have demonstrated the improved scalability of the statistical finite method using fractional stochastic partial differential equation representation of the Mathern fields. In general, these stationary and isotropic Mathern fields can be generalized to anisotropic and non-stationary Mathern fields. And in addition, using this fractional stochastic partial differential equation, it is very natural to define the Mathern fields on manifolds or curved surfaces. With that, I would like to conclude the talk. If you have any questions, feel free to send us.